Hi again everyone. In this simple video we're going to discuss Taylor polynomial approximations involving functions of two variables. Now, in first year you would have seen Taylor polynomials for functions of one variable, and hopefully you can remember that Taylor polynomials are a very simple and useful way of approximating complicated functions. Now, when we have functions of two or more variables, we can define and use Taylor polynomial approximations, and in particular their structure, their polynomial structure, make them easy to work with in the sense that they're easy to compute with. So essentially what we're doing there is taking a very difficult function and approximating it by a simple polynomial. But let's see how this can be done. Let's build our intuition a little bit. Have a look at the following example. Using an appropriate Taylor polynomial, compute an approximation to this value here. Now, firstly, we're asked to compute an approximation to this, but we're not told to compute it to within any specified accuracy. So that kind of leaves the question a little bit open. But what I'm going to do is put this in a slightly more general context and define a function based on the structure of what we want to approximate. So defining f in this way, what we would like to do, we wish to approximate f of 1.02, 1.97. Now, because we're not given any specified degree of accuracy for this approximation, the first thing you can do is, well, say, okay, well, 1.02 is nearly 1 and 1.97 is nearly 2, so if I replace with 1 and 2, I'll get square root of 9, 3. However, we can do a bit better than that. I'm going to use the most simplest Taylor polynomial approximation. Okay. Now the simplest Taylor, well, the simplest and most useful in many cases approximation is the following. Now, x0, y0 is just some point. Now, let me just explain some of the notation here. x0, y0 is just a point. Here we have the partial derivatives, and these lines with the subscript mean that each of these partial derivatives are evaluated at this point, and they're just multiplied by x minus x0 and y minus y0 respectively. Now, this right-hand side is known as the linear Taylor polynomial approximation. So, to f about the point x0, y0. Okay, so basically what this expression says is that for all x points and y points close to x0 and y0, f of x comma y is approximately equal to this right hand side. So we can use that information now to approximate this. Okay, so the first thing I would like to do is to choose x0 and y0 such that this right hand side is simple and the calculations involved are simple. So if I look here, well, 1.02 is almost equal to 1. It's approximate, well, it's close to 1. And 1.97 is close to 2. So I'm going to make a choice Now, if I look at the difference between x0 and 1.02 and y0 and 1.97, then I see that there's a small difference between the two that I'm going to denote by delta x and delta y, respectively. Okay, so what I'm going to do now for x equals 1.02, and this is just this plus this, and y equals 1.97, which is this plus this, I can take that and substitute in here. Okay. So over here we're going to have the following. Okay, f of x0 comma y0 is just going to be f of 1 comma 2. Then move on here, and we need to calculate the partial derivative with respect to x from this function here and evaluate it at the point 1 comma 2. So if I calculate the partial derivative holding y fixed and differentiating normally with respect to x, then I'm going to have something like this. And x minus x0, well, that's actually just going to be delta x, so I can just multiply everything by 0.02. And then I move on to this and I calculate the partial derivative with respect to y in this case, similar to what we had here. But in this case, we differentiate holding x fixed and differentiate with respect to y. And again, this will just become negative 0.03. So now I've got to clean this up. First of all, I'm going to substitute in x equals 1, x naught equals 1, y naught equals 2 in here, and then I've just got some simple calculations to do. So let's see if we can clean this up a bit. So substitution and simplification yields the following. Okay, so this first term is going to be the square root of 9, which is just 3. Over here we substitute in and we're going to get 3 on the top and 2 times root 9 down the bottom times 0.02, and over here we're going to get something like this, just substituting in. Now just simplifying all of this, you'll get 2.95. So let's test to see if we're fairly accurate here. We knew at the start that this was going to be something like 3, and I said we can do better than that. We've got this value here, 2.95, so we're a little bit more precise there. Now if we wanted a greater degree of accuracy, you could use a Taylor polynomial up to and including the quadratic terms. But let's actually look at the bigger picture here. The Taylor polynomial up to and including linear terms is usually a good starting approximation unless a greater degree of accuracy is required. And you may think, what's the geometric significance of these Taylor polynomial approximations? Well, basically what we're doing is think of the graph of a function of two variables being a surface. What we're doing is when we use the Taylor polynomial approximation, we're approximating the surface by a tangent plane. Okay, now it's important that you learn by doing. Here I've given you an example. Using an appropriate Taylor polynomial, compute an approximation to this value here. The solution method is very similar to the example that I've just presented.